about space with involutions. So yesterday there were talks by Hiroshi and Jake on involutions, and again this talk is again about this. So let M tau be a real space, namely a space with an involution. I will specify what kind of space and what kind of involution we consider later on. But given such things, you obtain a string theory called orientifold.
Sorry.
Yes?
Could you check?
The microphone?
No. Could you check? Sorry. Could you check your folders? Maybe somebody took my folders. Sorry. Go ahead.
Okay.
Yeah, you do microphone, so we couldn't hear you.
Oh, microphone is off, maybe? Oh, it's not a microphone, it's a recording. Oh, I see. So I should speak bigger?
Louder.
Louder, yes, okay. So we obtain some string theory called orientifold, and it is obtained by gauging or identifying the configuration space of the map from a world sheet to the target. So this is a surface, 2D. And another map like this, where omega is an involution of the world sheet, which is orientation reversing. For example, if you consider a closed string, say time t and space sigma, then the involution is like this. This is mapped to say t and say minus sigma. Or if you consider open string, say from 0 to 1, time and space, sigma from 0 to 1 goes to the 0 to 1 given by this map. Okay, so that's an example of omega. It's called parity. So this is called parity. So this is orientifold, identifies such maps. So this will introduce new maps, like a map from RP2 to the target, with or equivalently from sphere to the target, which is equivalent with respect to this say antipodal map and this tau on the target. Okay, so in a problem related to Gromov-Witten theory, it will be a problem. It will introduce a new problem of counting real curves. In this sense, the real in this sense. So there are many recent interesting works, starting with Welchinger and also Jakes, and also Johannes Walcher and company, is related to this. And one important ingredient in this orientifold is a fixed point set of the involution, if there's such a thing. Tau can be fixed point free, but if there's a fixed point set, this itself is an interesting thing, and this is called an orientifold plane. Orientifold plane. Y is a submanifold in the target, which is a component of the fixed point set, connected component of a fixed point set. And if you have n d-branes at Y, so if you have n d-branes in general at some submanifold, it will support UN gauge group. But in this orientifold theory, because of this identification of configurations, it will introduce a projection condition on this UN gauge group. And the gauge group is either ON or USBN. Maybe in the standard notation it's SBN over 2. So n has to be even. So SB1 or USB2 is equal to SU2. So there are two types of orientifold plane. So either ON or USBN, and this is called the type of orientifold plane. So this corresponds to O minus type. So I'm introducing a type here, and O plus type. So these two possibilities are possible. Okay, so this is a very brief introduction to orientifold. And I want to specify this class of theories, string theories I want to consider. And you can consider many things. Perhaps for most of you, most interesting thing is what we call topological strings. Namely topological A model, which is the Gromov-Witten theory, or topological B model. But I want to consider something related to this but different. So this is so-called type 2 superstring. And orientifold obtained from it is called type 2 orientifold. And for this M has to be 10-dimensional Riemannian manifold of signature pseudo-Riemannian manifold of signature 9 plus and 1 minus. So 9 space and 1 time with a chosen spin structure. So for this signature you can have real spinners, Marano spinners, and also wild spinners are possible at the same time. And tau is an involution, and we require that it lifts to the real spinor bundle. So it's called spinor bundle S of M, tau tilt lift to the action on the real spinor bundle. And you can consider you can have 4 cases. Such involution can be classified into 4 cases. So tau is either orientation preserving or orientation reversing. And the lift squared can be either plus identity or minus identity. And I just name these four cases B plus, B minus, and A plus, A minus. And if you're familiar with string theory, this B corresponds to type 2B string theory. Type 2B. And A corresponds to type 2A. So if you consider Calabi-Yau threefold times four-dimensional Minkowski space, then this 2B and 2A are related to B models and A models in topological strings. And possible O-planes. So for B plus, you have codimension equal to 0 mod 4. And for B minus, it is 2 mod 4. And A plus, this is 3 mod 4. And A minus, it is 1 mod 4. And you, yes?
When you say type 2D, where that's before you do twisting.
Before you do twisting, what do you mean by twist? Topological. Ah, yeah, this is before twisting, yes. Yeah, and we have actually jargon for naming these O-planes just by counting the dimension. And if you have this codimension K, I call this codimension K O-plane, I call it O9 minus K plane. Just counting the spatial dimension of the O-plane. So if K equal to 0, the codimension is 0, space-time filling, it is called O9 plane because the dimension is, space dimension is 9. Because 9 is the space dimension. So this is the case, this corresponds to either O9 or O5 or O1. And this corresponds to O7 or O3. And this corresponds to O6 or O2. And this corresponds to O8 and O4 or O4 or O0. O0 corresponds to a point. And for Gromov-Witten theory, this O6 case is most interesting. And for the B models, there are two kinds of things, either O5 or O7, O3, both are possible. Okay. Are there questions so far? Okay. So what I want to do from here is to see what kind of projection condition you get, or condition you get for the D-branes and or open strings in these theories. So let me just briefly describe the data to specify D-branes before Oriented folding, first of all. So D-branes in type 2 string theory. So on M, say on 10-dimensional space-time M. So there's a uniform, systematic way of constructing D-branes out of some data given by space-time filling branes. So for this, you need to have E, a Hermitian vector bundle on M, and A unitary connection of E, T, Hermitian endomorphism of E. And so depending on 2A or 2B, corresponding to this case eventually, 2A, this E is ungraded, and for 2B graded. So E has even part and odd part, and A is of this form. A is even and T is odd, say this form. And so if you require some additional conditions, say A has only 1,1, so say M has some part which is say Calabi-Yau manifold, and A is 1,1 curvature, and T is holomorphic. A part of T is a holomorphic. Then it specifies say a complex of holomorphic vector bundles. And
so
for
you need to assume any two supersymmetry?
yeah, at this moment you don't need. I'm talking about the general type 2 strings, but for the yes, well, actually for some space-time supersymmetry, say which is relevant for the say 4-dimensional compactification, you actually require yes, wall sheet supersymmetry n equal to 2, 2 for the sigma model, and also for the branes some diagonal n equal to 2 supersymmetry. Yes, and for that you need certain condition, like this determines a holomorphic complex of holomorphic vector bundles. And for A model, for type 2A, it's more indirect. Roughly speaking, the zero of T, the locus where T is non-maximal, T have non-maximal rank, T is not invertible, is a place where the D-brane is. So you can consider, if you consider D-branes on special Lagrangian special Lagrangian submanifold, that should correspond to some E and T and A, where the zero of T corresponds to this special Lagrangian.
So U and U1 have the same rank?
For this case, you don't have to have. Yes, but yes, you don't need this rank to be the same. Now we would like to find a condition for this data to be D-brane in this orientifold. So condition of orientifold projection for this data. So first of all, you want to study what kind of action, this orientifold action, what is the orientifold action is for this data. Okay. Okay, so on this EAT. So first of all, so I want to recall this map. So this part, left boundary is mapped to right boundary, and right boundary is mapped to left boundary. So it should involve transpose of these matrices. Actually, this open string, this roughly corresponds to open string field. And the reason why you have this matrix form is coming from this, say, if you have if you label this boundary, actually you have several. You have vector space attached on each of these boundaries, and that corresponds to this vector bundle E. And you can label this element of the vector space by some label I and j, and this is swapped, I and j to j, I to j to I.
Is this a worksheet?
I'm looking at the world sheet, yes. Strip, open string. I'm sorry if this was not clear. This is important. So this should involve a transpose, and also this tau. So I'm gauging this x to tau x omega. I'm talking about this omega part here, but also this tau part. So A should map to tau star A transpose. But of course, if you have a transpose, the natural thing you do is to take the minus transpose, and that would correspond to E to tau star E star, and T, same for T. And for this case, there is no a priori reason to assume which sign you should take for this T. So this is the natural guess. But there is something else you can do, or actually sometimes you are forced to do too. It is to shift the gauge field by another gauge field, which is a gauge field of a U1 connection, a U1 line bundle, connection of a U1 bundle, so tensor with some line bundle L. So that's the natural thing you can do. And the reason let me explain why you need to do in some cases. Well, actually you have to choose some connection, line bundle with a connection. And this alpha is actually related to the B field. It doesn't have to be flat. It depends on the B field. So alpha is constrained by the B field B. Let me just give an answer. B plus tau star B should be equal to D alpha. So let me first remind you what a B field is. So if you have a B field, you have a action, or the string action should include this term. Okay? And this is mapped, if this is done, and this is mapped to, of course, to tau x omega star B, which is of course omega star x star tau star B. And because omega is orientation reversing, it is equal to minus sigma x star tau star B. Okay? And so the net change is the difference of the transformed one and the one before the transform. So the change is minus x star B plus tau star B. Okay. So suppose you consider a wall sheet without a boundary. Then what you need is that this action enters into the in our language path integral weight, and we don't want this to change, so this is equal to 1. That's what we want, and that requires this to be an integral times 2 pi cohomology path. So we want this to be to determine an element of 2 pi z. Okay. So in other words, so that means that you can write down this to be some first Chern class of some line bundle. Maybe let's put minus here. In other words, there's a U1 connection alpha of some bundle, of some line bundle, such that this equation is satisfied. I'm not yet seeing the relation between this alpha and this alpha yet, but I'm just saying that there should be some alpha like this. And to see that this is required is you can see by looking at this wall sheet with boundary. So now we require this existence of such alpha. So that's a condition for B. So B field is not arbitrarily, but it has to obey this condition. From this consideration of this invariance for this transformation to be a symmetry of the closed string theory. Now, given that, you can find some alpha like this. Now let's consider an open string. So this, if it does have some boundary, then the shift part, you can use this expression here, is d alpha sigma, and by Stokes' theorem, it is like this. So it shifts the action by this factor, and this is indeed this introduces the shift of A by alpha, because this if you have a gauge field on the D brane, then the action includes this. The total action should include actually a holonomy factor, in physics language it's like this, times some other factor. So this is a holonomy factor. It's a parallel transport, and then take the If this is the parallel transport with respect to A, and if you have a boundary like this, then if you have a term like this, this will. I'm sorry. This is to you just have to pull back. Take the pullback connection, and then take the holonomy along the boundary. And having this does do the shift like this. Okay. So alpha has to be. If you have a B field, then it necessarily with B field with such alpha, then it necessarily shifts the gauge field. And there can be many such alpha, and you have to make a choice. Actually, this choice is important. But let's see. Yeah, I will explain what kind of choice is. Sorry. So this is the choice you have to make, but there's actually also a gauge transformation of these choices. So the choice is not that many. So if you just require this condition, then there are infinitely many alphas you can consider, but actually up to gauge transformation, there are not so many choice. I will talk about this gauge transformation later. So this is the action on this data, on the data. Now I want to also describe the action on the more general open string state. Yeah. So action, orientifold action on open string state. So first of all, what is an open string state? Phi is to assign a string configuration, say a map from, say, 0, 1. Now I'm just talking about just this string from 0 to 1 to the target. So fixed time, at a given time you have a map from 0, 1 to the target. So it's a wave function of this such open string configuration, phi of x. And phi of x lies in homomorphism of a vector space between this vector space, the fiber at x0, fiber of E at the initial point, the image of the initial point, to the fiber of E at the image of the ending point, the final point of the string. So that's the open string state. Okay. So we want to find a parity action on this open string state, orientifold action on this. So again, because there's orientifold exchanges left and right, it has to involve the transpose of this phi of x. So a natural action would be, so from phi of x to, I call P of phi of x, which is just take phi, and this argument, you just consider this transformation of this open string configuration. Now omega is 0, 1 to 0, 1, and sigma to, say, 1 minus sigma. And then transpose. And that would lie in home, because the transpose, you have a swap of this entry and the dual, and tau x omega 1 tau x omega 0. But of course this is tau x 0, and this is tau x 1, and therefore this is tau star E star x 0, and this is tau star E star x 1. Okay. But this is not something you want, because this, what you want to have is a string state between the image brane. The image brane is this, not just tau star E star. So what we really want, so this is a first attempt. What we really want is to be in home and tau star E star tensor L, and then x0 tau star E star tensor L and x1. So there is a gap between this and this by this factor. So the gap is the gap is this factor L x naught L x1. Okay, but there's actually a natural thing that fills this gap, which is to use this connection. So there exists a natural candidate to save it, and this is to use the parallel transport using with respect to alpha. So I just so let me just rewrite. I need this. Yeah, maybe not anymore. So what I want to write here is phi of tau x omega transpose, and also take the parallel transport, so it's exponential of minus x star alpha from 0 to 1. That would be an element of this. So you have that right hand side is an element of this. So you obtain what you wanted. Okay? So that's the parity transform of the open string state. But what we want to do is to find invariant string state. What I wanted is a map parity action, the orientable action on open string states from one space to the same space, so that you can select the invariant state. So what I really want to have is a wave function taking values in this, actually. So what we really wanted is not yet this one, which is in this space, a different space, but what we want to have wave function which takes values in the same space, is some p of phi for our open string configuration X, which belongs to the same one. So on x0, x1. So whereas this belongs to that one, let me just write again. Okay, so you would obtain such a state if there's a map from here to here, and that map should also transfer this parity image data, so to the original. So for this we need an isomorphism. From the transformed the orientifold image plus or minus t, so isomorphism u, to this. Okay, so that would be obtained, for example, by taking a unitary bundle map from this to this, such that this connection is sent to this, and this endomorphism is sent to this. So we want such things. And suppose you find such things, then you can define this P of then. If you have this, then you can define this parity by conjugating with U. This would be an element of this. Okay? But it's not just what this is not still not sufficient. What we need is a parity that has the same algebra as the original transformation, which is, for example, if you take the parity squared, you want this to be identity. So that's the another thing we need. So we require the algebra P squared equal to identity. So let's just compute P squared of phi at x. You just follow this definition and then do this algebra. Then let me just write down the answer. Only the answer. U of x1 and U of tau x1 transpose and then inverse, and phi of x tensored with this holonomy parallel transport factor 0 to 1 alpha minus tau star alpha, and then composed with U of x0, same kind of things, tau x0 transpose inverse, and then the whole thing inverse. So that's the P squared of phi, and we want this to be equal to phi of x for any phi, for any open string state. Okay, so that would require some condition between this and this. We want this to cancel to get along with this. So this P squared, this requires condition U tau star U transpose inverse to be equal to C times identity, where C is a section of the line bundle tau star L tensored L inverse, such that C of x1 tau transport alpha minus tau star alpha C of x0 inverse equal to 1 for any string configuration mapped from 0 to 1 to m to the target. So this condition means that C is actually a parallel section of a connection with respect to the inverse of this thing. C inverse is a parallel section of a connection with respect to this line bundle, inverse of this line bundle with respect to this connection. So by E, C is a global parallel section of this bundle with respect to the connection tau star alpha minus alpha. So yeah, maybe I didn't say it correctly before. Alpha is not arbitrary. Alpha has to obey this condition, namely this combination should be flat and no holonomy along any loop. Okay, so this is a strong condition on alpha itself. So this comes from this requirement that this p squared is identity. And this C has to do actually with this, actually to look, if you look at this, C determines the, if you consider at some fixed point set, tau equal to tau fixed point set, C determines whether U is symmetric or not. And this has to do with the type of this orientifold, whether the projection is ON type or USB type. So let me comment on that. So O-plane type. So at an O-plane, namely a component of the fixed point set, there is a canonical isomorphism between L and, of course, tau star L. Canonical isomorphism. And this C also defines an isomorphism. C also defines an isomorphism, actually everywhere on the target space. And this actually agrees with this only up to sign is equal to it on Y is equal to it up to a sign. If you use this, then at fixed point set, C squared is equal to 1 is what you see. And C squared equal to 1 at the fixed point set. So plus or minus 1. And this corresponds to the O-plane type. Okay, I'm not saying this plus or minus corresponds to O plus or O minus. There's some certain rule depending on the dimension. And maybe it makes not so much sense so to write the list, so I don't write it. But essentially, either plus or minus corresponds to either O plus or O minus or opposite. Okay. So another thing I wanted to say is this gauge transformation. That identifies the data. So gaze transformation of this data. So the data for the orientifold is B field, L, alpha, and C. And this may be identified with so-called B field transformation is like this. So let's take L lambda, a Hermitian line bundle with a unitary connection. So B is shifted by the curvature of the connection lambda, and L is shifted by tensored with L, and alpha is shifted by this, and C is untouched. Or also another thing is ordinary gaze transformation of this line bundle L. L alpha plus this, and C is also changed. Lambda tau star lambda inverse C. So this is the gaze transformation. So if these data are related by this, they can be identified. And this corresponds to the following transformation of this D-brane data. So D-brane data now has this U isomorphism. This is transformed according to this by E tensor L. A is shifted, and then TU. Or under this is E A T, and then U is multiplied by this gaze transformation, lambda. Okay, so this is the so this is the gaze transformation of this orientable data. Okay. Oh, I have 5-10 minutes only for the mirror symmetry part. So are there some questions about this? Okay, so let me just consider more special theory, which has a part which is described by a sigma model with a 2,2 supersymmetry. Symmetry.
So far you don't need dimension 9 plus 1.
You only need dimension. You only need this dimension 9 plus 1. And
I don't see any dimension 10 coming in.
It's from the completely different things. So this is to define. So I gauged by orientation reversal, but before that I should have gauged also ordinary orientation preserving diffeomorphism, and that is possible in 9 plus 1 dimensions only. Yeah. That's the yeah. I have many. There are many things I haven't explained today. I'm sorry. This is This is about the fact about type 2 superstrings, and I of course did not have time to explain all of these. Okay, but let me just. Can I go on with this? Okay. So let's consider a special case to the 9 minus 2n plus 1. So this is a Kähler manifold of complex dimension n. So actually, what we need is there's an additional condition like Ricci flatness. So Calabi-Yau or torus is what we have in mind. And then this sigma model, for this internal part, sigma model on X has n equal to 2, 2 supersymmetry. And then if you wish, you can twist the theory to obtain the topological field theory. And also you can also consider topological strings, and that plays some role in obtaining some important quantity in this type 2 string, 2 superstring. And this involution tau, let's focus on this part, preserve half of it, half of the supersymmetry, so-called n equal to 2 supersymmetry. If tau is either holomorphic involution or anti-symplectic or anti-holomorphic or anti-symplectic involution. Symplectic with respect to the Kähler form. Symplectic. So this is for the B model, and this is for the A model. If you consider Calabi-Yau threefold times R4, then this can be used for type 2B or type 2A orientifolds. So anti-symplectic for Calabi-Yau threefold is, of course, orientation reversing. And the mirror symmetry relates this. So the mirror symmetry X tau, X hot tau hot. So if it is holomorphic, and then this is anti-symplectic. And of course you have to put additional data, and then also have to put additional data. And if I have time, how many more minutes do I have? 2 minutes, okay. Let me squeeze in, let me try to show you some example. So example is X is the 2 torus, R2 mod Z2. Let's just write the coordinate of R2 by X and Y. And actually there are 6 distinct involutions. One is X, Y to X, Y. Identity. Okay, maybe I don't have. I need to. X plus the shift of one coordinate and inversion of one coordinate, inversion of one coordinate and shift of the other, and exchange of coordinate and inversion of both of the coordinates. And this is orientation preserving. So orientation preserving or not? If yes, it is B. If not, A. And the O plane is the entire T2, and there's empty, and this is empty. S1, two S1s at X equal to 0 and 1/2, and empty, and this is one S1 at X equal to Y, and 4 points at X and Y equal to 0 and 1/2. Now the B field, oh, I will have trouble writing. So B field. So I'm just writing down these possibilities. All plane types. All types. So for this, so it is either 0 or pi dx dy, and it is trivial, and this is O minus p, with p is anywhere, for any p. P is a point in the torus. I'm choosing holomorphic coordinate, complex structure, and then writing this in terms of this homomorphic line bundle. But all of these are equivalent. And you have all plane types, O9 minus, O9 plus. And this is again O9 minus, O9 plus. So this would, if you put ND branes, then you have ON and USPN gauge group. So that's the first case. This is the first case. The second case is 0, trivial, and empty. So CZ. And the third case, B field is arbitrarily, and the line bundle is either trivial or the two torsion. And in this case, O8 minus, the two circles, so both of them are O8 minus, both of them are O8, either both of them are O8 minus, or both of them O8 minus, and in this case, O8 minus plus O8 plus. One of the circle has minus type, and the other has plus type. And in this case, trivial. So this is arbitrarily, trivial, and no all plane. And in this case, again, arbitrarily, trivial. So there's one circle, so just one O8 minus or O8 plus. And in the last case, there are two values possible for the B field, either 0 or pi dx dy. And for the twist, it's either trivial or two torsion. And in this case, there are O7 minus, four points are all minus type or all plus type. And in this case, two of them are plus type and two of them are minus type. And in this case, this is O minus P, where P has to be at the fixed points, one of the four fixed points. And so we have, in this case, there are one out of 4 or 7 planes. One is plus type, and this is at point P, and the rest is minus type, or the opposite at P, and the rest is plus type. Okay, so that's the classification, and they are related by mirror symmetry. So the easiest is this. So this mirror symmetry relations. Or T-duality or mirror symmetry. So this is related to this. These are related to these. And then again to to this. Or this more interesting case, the vector without vector structure is related to, no, not yet, sorry. Maybe this, so this is related to this two torsion. So the shift orientifold is related to this two torsion. Or this is one, so this is mirror symmetry or T-duality in X direction. Or if you do the T-duality in Y direction, you get another thing, which is this. Okay, and then this is also related to this, or this is related. Oh, I'm sorry, this is not. Yeah, these are both. This is related to both to this. And the final, the most interesting is this one. This is related to what's not written, which is this. This and also this. So this is the mirror symmetry relation. Maybe I don't have to explain the reason, but you just have to look at this, how this orientifold acts on the gauge field. So that so in this case, T-duality or mirror symmetry is easy to see because the coordinate in the T-dual is related to the gauge field of the original. So you just have to look at this action on the gauge field to see how it acts on the coordinate and vice versa. So that's all I wanted to say. Thank you very much.